Okay, I'm going to get started in the interest of time and making sure we have enough time for plenty of questions and chatting afterwards. So firstly, thank you all so much for coming. My name is Dr. Helen Coulshed. I'm a senior lecturer in chemistry education. I'm also the chair of the Natural, Mathematical and Engineering Sciences Equality, Diversity and Inclusion Committee. Wow, that's a long name. So I'm the human that keeps emailing you about cool things that we're doing in our faculty and ways you can get involved in EDI work more generally. So today is Ada Lovelace Day, so happy Ada Lovelace Day, everybody. And we've got a fantastic speaker that we will hear from shortly. And Dr. Calliope Milano will introduce them shortly. But I guess one of the things that I want to talk about is like why are we here? So Ada Lovelace Day obviously is a celebration of one of the first known female computer programmers. But the key thing is it's part of a larger week, so part of a larger initiative, which is Women in Science Week, which actually this year extends to a fortnight, which is very exciting. But as we know, women are underrepresented still in science and engineering. So the reason why we do things like this is to encourage women to come together and share their stories, and also to talk about some of the excellent things that women are doing in science already and will continue to do, obviously, as well. So this is just one part of a larger program. So I'd really encourage you to get involved and find out what your department's doing as well as what the faculty's doing. But yeah, to say that, whilst things are better, we're by no means where we want to be. We definitely don't have parity in terms of female representation, both at undergraduate or staff level. And underrepresentation extends beyond gender, as we know, and we need to be very intersectional in our approach for inclusion. Okay, so this is by no means, where we want to be. We know that we've got work to do, and that's definitely what we're actively doing at the moment. If you want to know more, if you want to be involved, please do get in contact with me or your EDI leads in your department. But yeah, thank you all so much for coming, and yeah, I hope you really enjoyed the talk. So I'm going to hand over now to Calliope. Thank you.
Thank you, Ellen. Hello, everyone. I am Dr. Calliope Milona, and I'm a senior lecturer in statistics here and also the EDI lead for the Department of Mathematics. So I'm very happy to introduce today Dr. Eugénie Hunsicker, who is a mathematician. Her research lies at the intersection of analysis, geometry, and topology, and she has also worked on more applied topics in data science and image classification. In 2018, as chair of the London Mathematical Society Women in Maths Committee, Eugenie worked with filmmaker Irina Linke to produce a short film on faces of women in mathematics. She has received several awards, such as the Trevor Evans Award of the Mathematical Association of America and the Suffrage Science Award for Mathematics and Computing. She was elected as a fellow of the Association for Women in Mathematics in the class of 2021. Eugene, the stage is yours, and we are very happy to have you here today.
Thank you for that kind introduction. Let me see if I can figure out how this works. Ah, there we go. Okay, that's me. So this is the topic I chose for my talk, reinventing my career as I go. And I sometimes like to say, rather than having a discipline, that I'm actually an undisciplined mathematician. And I want to talk to you about what I do and what that's been and how I've done that and what your choices are, how you can do a lot of cool stuff in your life too. So this is sort of a general slide about some of what I do. So I'm a mathematician, but I recently moved from academia into a job in industry. I work for a software company called the Access Group. So that's me and my friend Sara Lombardo on a run. We went up and stood outside and took a photo of ourselves in front of the building. It's a beautiful, big building just on the Loughborough University campus. So I work there 4 days a week. And in my 5th day a week, I do a variety of things. So for one thing, I have a set of not just four, several PhD students that I co-supervise at Loughborough University. And there are 4 of them that you can see there saying hi to me at an event. They sent me that shot of themselves, which was really sweet of them. So they're in a range of different areas related to data, and I would say sort of statistical metrology, and I'll talk a little bit about that later. Also related to that, I'm involved sort of tangentially with the spin-out Figura Analytics, which is a company that's developed a new way of analyzing particles in solution. And so I was involved with that research on signal processing and signal inversion and metrology for that instrument. So I get to find out about that as well. And then I'm also very involved in equality, diversity, or equity, diversity, and inclusion work. So I'm the chair of a group called the Athena Forum, which is a sort of umbrella organization that brings together professional societies to talk about how they're meeting the challenge of diversity in their areas. And then I'm also the honorary officer for equality, diversity, and inclusion for the Royal Statistical Society. And there I am with their CEO, Stian. Okay. I'm going to talk a little bit more, advertise for my fabulous company. I absolutely love working there. So Access Group, you may not have heard of it. But it is actually the largest software company headquartered in the UK. We're a business-to-business software company, so we provide software solutions for whole range of industry. We've got over 5,500 employees, growing very quickly. Our goal is to be at around 12,000 by 2026. It's a multinational company. We've got employees on several continents and all kinds of areas. So, I mean, just any area that you might think there's somebody working in that area. So obviously software engineering, but sales and marketing, also user experience and design. There are people who are working in human resources areas on diversity things as well. I don't know. Big companies have people in pretty much everything. So it's a great place to work. I really, really recommend it. Keep your eyes open. So you can see we've had 15 years of uninterrupted profitable growth with over 680 million in revenue last year. So quickly growing and great company. So I work in something called the Data Solutions Center of Excellence, which is a new area aimed at trying to use the data that we have, that we get from our software solutions, to help companies with what they do. So we've got three groups within the Data Solutions Center. So I think when people think about data science, a lot of people don't really know what sort of things are involved, but these are three sort of main areas. So one is data engineering and architecture. And these are the people who set up the data environment. So we've got an Azure environment, so a cloud data environment. There's all kinds of issues around infrastructure, compliance around security of data and use of data, and all sorts of things that we have to make sure are embedded well into the way that we work with data. We also have a data analytics and business intelligence group, and they are developing sort of visual and numerical summaries of all kinds of things to help people make business decisions. And I lead what's called the data monetization group, where we're developing modeling tools internally and also within our products. And Access works across a large number of sectors: hospitality, recruitment, health and social care, legal, education, not-for-profit, supply chain, etc. So there are a lot of places that we can use data to try to improve the way things are done. In hospitality, for instance, how can we reduce the waste, food waste in restaurant industry? In recruiting, how can we embed more equitable recruitment practices? Health and social care, as you know, we've got an aging population. More and more people are requiring support in homes. How do we ensure that we've got the capacity to support those people? You can imagine sort of all those other things. Oh, supply chain, a lot of questions around carbon footprint. How can we reduce the carbon footprint of companies? So there are a lot of ways that data can be used to really drive ethical and moral improvements. And that's something that's really important to me and to Access. So our vision is what I call intelligent solutions for sustainable success, where we're trying to merge business intelligence and artificial intelligence in order to have sustained business success at Access, success for our customers, but also business that's sustainable for the planet and humanity in terms of the UN Sustainable Development Goals. So this is where I work. I don't just work, I do other stuff too. So I've got three kids. You can see them there with the horns. That's Esubalo. In the suit, that's Bereket. And with the puppy is Asrat. His puppy is called Ace. That's my grand puppy. I'm there with my dog Carlos and my ukulele. That's a tea set that I made. I love doing sort of arts and crafts stuff when I've got the time, not very much. I play the fiddle. We've got two rabbits. That's Newton, named after the unit of mass, not the person. He's a continental giant. He's very large and heavy. And then up in the corner is Bucky. She's the little bunny, so she's named for Buckminster Fullerene. Anyway, and that's my husband and I with our dog Polly. So a full life. So how did I get here, right? How did I end up with this weird, large set of different things that I'm doing all at once? Well, there's a book called Women Becoming Mathematicians, which is a great study of women mathematicians in the US up until about the 1960s. And she talks about the ways in which women's careers are often different from men's careers, or have often been different from men's careers. And she talks about this thing called the myth of the mathematical life course, which is characterized by early recognition of talent and an uninterrupted path to professional success. Right? And we hear this narrative very often in citations for mathematics prizes, right? If you read any of the prizes, or any prizes, right? There's a lot of this, so and so was recognized as a genius at the age of 3, and et cetera, right? It's a very common narrative. This is not the story of my life. Okay, so that's my life. Well, this is my CV, so you can make it look okay. So I got my Bachelor of Science degree in mathematics from Haverford College, a small liberal arts college in Philadelphia. Then did my PhD in mathematics at the University of Chicago. You'll notice that there are 7 years in between those graduation rates. That's because it took me 7 years to do my PhD. And I thought that I was a terrible failure the whole time. And then after I finished, I found out that was the median time to completion of a mathematics PhD. But nobody told me that. So anyway, interesting what they don't mention to you. Then I went back to a liberal arts college, a small teaching university called Lawrence University in Wisconsin, and I taught there for about 6 or 7 years. And then I was promoted. I got through tenure, this ghastly, horrible process in the US of tenure. And then I left immediately to come to Loughborough University as a lecturer in mathematics. So going from where I'd been at the sort of associate level back down to the very bottom of the pile. And I was a lecturer for a good long time, you can see. During that time, I had a year of adoption leave. And I also changed my research area at that point, just completely diametrically changed my research area. So finally, I was promoted to senior lecturer and started in this new research area. And then by the time I'd sort of gotten success and was promoted to the next level of reader, once again, I left that very year to change my industry, change to a role in industry. So it's a little bit of a strange way to go about things, but it's worked. It's worked. Okay. So anyway, early in my life, I was not a child genius. That's me, my untidy blonde hair, not so very different from the untidy hair I've got today. And you can see I've got my guitar. I've changed to a ukulele now, but yeah, you can sort of see the similarity. I wanted to be a paleontologist. I used to pretend to dig up dinosaur bones in my backyard. And then from about 12 to 19, I wanted to be a doctor. My dad was a doctor. He's a medical researcher, and I really wanted to be a doctor. And then at some point, I was thinking, maybe a psychiatrist. And actually, this is really interesting because it was just at that point in time where the new non-invasive medical imaging techniques, magnetic resonance imaging, was coming in. And so you see, we've got these pictures of brains on our T-shirts. And this is from a summer I worked in a psychiatry lab, basically doing image analysis of MRI. So it was really interesting time to be looking at psychiatry. Anyway, during my undergraduate degree, I also had the opportunity to spend 2 summers doing research, doing a summer research bursary with my supervisor, Curtis Green, who's a combinatorialist. And together we put together this computational mathematics package in Mathematica. So again, this was one of the very first, very beginning of computational mathematics, computational exploratory mathematics as a research area. So how can we, do numerical experimentation on pure mathematics topics to allow us to generate conjectures that we might then try to prove. And now my next slide has a theorem on it. Okay, so this is something. This is the one part of real mathematical content. This is one of the things that I think is so quintessentially beautiful about mathematics, is the way in which surprising connections can be made between areas that you think of as why should those things be related? And yet there's this very deep connection. And combinatorics has this fantastic, beautiful trick called double counting. This is a proof technique in which you count the same thing in two different ways. And that allows you to get to some really surprising inequality. One example of this is this equality here. So for those of you who are not familiar with this, on the right-hand side, of course, we've got 2 to the n, 2 to the nth power. That's 2 times itself, n times. On the left-hand side, we've got a sum of all of the what are called binomial coefficients. So we read that thing in parenthesis where the n is over the k. That's read as n choose k. And that's the number of ways to choose k balls out of n, right? So if you just think, how many different ways can I choose? Well, if we've got, or n people, how many ways could I form a committee of 4 people, right? How many possible committees of 4 people are there amongst the people in this room? That would be an example. Okay. And on the surface, it doesn't seem like these should be related, but you can think of them both as calculating the number of subsets of a set of size n, right? So if you've got 10 people, for instance, how can you think about how many possible committees you can create? Well, one way is you can say, well, the committee's got to be some size, right? And for each size of committee, there are, for each size k of committee, there are n choose k ways of choosing that committee. And so you sum over all the sizes k, and that's got to be all the possible committees you could form, right? On the other hand, with 2 to the n, you can say, well, there's n people, and in any given committee, everybody's either in that or not in that, right? So you've got n choices of yes or no, and that gives you 2 to the n. So when you write these out, it's not at all obvious that they should be the same thing. But if you think about them in just the right way, it becomes almost obvious that they are the right thing. And I always thought that that was something really beautiful and deep and remarkable that you get in mathematics. That is, I think, really something that draws a lot of mathematicians in. Is a really beautiful thing. When I was 22, I started my PhD in mathematics. I'd had this inspiring chance to do mathematics research. I'm like, oh, I'll give it a try. My mom was asking me, what are you going to do with mathematics PhD? I wasn't quite sure at the time, but I just thought I'd give it a go. And when I was in graduate school, I was working on a sort of area of mathematics it was actually related to string theory. I was a string theorist out here in your department. And this was about general Hodge or signature theorems. But Hodge theorem is if you've got some sort of abstract mathematical shape, which is called a smooth manifold, that has particular structure at infinity, which is called a manifold with corners, then it's any sort of relationship between, on the one hand, the kernel of the Laplacian for some metric on some set of differential forms, and on the other hand, some sort of cohomology of a complex defined over a related space. Now, that's a lot of probably incomprehensible jargon, but what you can take out of that is, on the one hand, it's something related to partial differential equations about how heat travels on objects. And on the other hand, it's something about what happens if you cut and paste that object. What sort of pieces do you get and how do they fit together? And once again, it's not obvious that those two things should be related. And it's, again, this fantastic link between two really disparate areas. So after graduate school, after my 7 years of graduate school, in which I really found research quite a struggle, I decided maybe I'll go to a teaching intensive place. So I went and worked for 7 years at a teaching intensive university. That's me with the sunglasses and the pink robe. And let me tell you, there's one thing is you do get a lot of use out of your PhD gown when you're working at a liberal arts college. You get to wear it over and over and over again. A lot of fun. My PhD supervisor used to go to graduation in his PhD gown with nothing on underneath. It's very hot. Okay. Anyway, so, all right, as I said before, I got tenure and I was promoted in the spring. I got married. That's my husband, Josh. And then we moved to the UK to start over as a lecturer. And this was because although I loved teaching, I also was finding that I was enjoying research more, especially after I didn't have to do it all by myself, hitting my head against the wall by myself. And I found it was a collaborative activity. I really enjoyed it a lot more as a collaboration. And so I wanted to go somewhere that I'd have the chance to do more research. So when I got here, um, I didn't want to just do the same thing I'd done the whole time. Um, I wanted to try to branch out and do some different things. So I took some of the pieces that went into these Hodge theorems and I sort of looked at them separately. So on one hand, I did some work on pseudo-differential operator theory, which is sort of about how to study things like heat flows on complex shapes. I looked at some singular finite element methods as sort of numerical methods for studying differential equations, again, on shapes that have, they're kind of weird shapes. And then some stuff, topology of stratified spaces. And again, this is just sort of this cut and paste sort of methodology. And in some sense, I was branching out, but I was also sort of trying to put down new roots in a new country where I was sort of away from the group that I had been involved with as a researcher when I'd been in the States. And that was okay, but I found it, again, a little bit of a struggle. So, as I said, in 2010, my husband and I adopted 3 kids, and I had a year of adoption leave. And it turns out that being a mom, it takes a lot of time and energy. Being a dad too, being a parent, the kids are exhausting. I mean, they're great, but they are exhausting. Don't make any bones about it. And it's also really hard to find extended periods of time to concentrate. And when you're trying to do something that's very sort of deep theoretical work, where you have to do sort of long calculations that you're able to concentrate on, I found that if I didn't have at least a week to concentrate, I couldn't get anywhere. And I didn't see in my future a lot of weeks in which I was going to be able to concentrate at the level I needed for the stuff I had been doing. So even though I had enjoyed it, I also found when I had kids that I started wanting to be able to explain to them why I did what I did. Why should they care about what I do? That became really important to me. So between 2011, I don't know whether it was 2000, 2015, I don't know, some period of time now still, I felt really like I was jumping across a chasm. And I transitioned from pure mathematics to applied statistics, and not even just sort of applied statistics, but like really kind of very pragmatic, sort of like the engineering of data science, right? Um, and I looked for this jumping across the chasm, and I found that there are a lot of men, a lot of white men in business suits that seem to do this quite effortlessly. Um, I was frantic the whole time. I always was like, I'm not going to be like those guys. I'm going to be like Waffles the Terrible, who not only has had an epic fail jump from the car to the ledge there, but has had it viewed over 10 million times publicly. So it was very scary to do this sort of total transition. And I had, there was sort of the two sides of it. On the one hand, when I talked to some of my colleagues from analysis, they were like, "Oh my gosh, what are you doing?" On the other hand, when I talked to my husband's PhD supervisor, who was an engineer, said that I was changing from mathematics to statistics, he was like, "What, is there a difference?" So we can get very siloed sometimes in science. Anyway, so it took a long time, right? So once again, sort of 7 years of struggling at this, right? And I started out, okay, so I wanted to change to doing statistics. I had never actually taken a statistics course before in my life. So of course the first thing I did was offered to teach statistics, because they always need people to teach statistics. Every university always needs people to teach statistics. They'll take anybody. You don't ever have to have cracked open a statistics book before. This was definitely the one page ahead of my student situation. So I started teaching and learning undergraduate applied statistics. I became immediately the program director for the new mathematics statistics program, having to not only create classes but design the whole program. This is a very steep learning curve. So I decided, what I'm going to do. I did a bunch of undergraduate projects, both undergraduate summer projects and undergraduate final year projects, where they just did all kinds of different things. I didn't care whatever topic they want to do in statistics. I'm like, okay, I'll supervise it, and it was fun actually. We learned a lot. They were interesting projects. Um, anyway, so in about 2016, I was starting research collaborations, and one piece of advice that somebody gave me that was really good advice is that when you're trying to find a new applied thing, don't feel like you have to go with the first thing that people present to you. Look around a bit and find out what sounds good. So, but I did, even the very first one, I started working with chemists, and I found that was fantastic. I loved working with chemists because chemistry is just that bit more complicated than physics, that it's hard to really just do it mathematically from first principles, right? But at the same time, it's not so broad as biology that you just kind of want to forget about all of that. It's sort of somewhere in the middle. It's this area of complexity where we're starting from both the data science side and from the modeling side. We're starting to be able to really come in on what's going on in chemistry, and it's just absolutely fascinating to work on this. Um, and the other thing is that, I really found that even though I had been a hopeless experimentalist when I was a student, when I took any sort of science, I was desperately bad in the lab. I loved working with experimentalists. So this is how I ended up working on this project that led to the spin out. And this is an area of electrochemistry called resistive pulse sensing. So originally, this is a method of counting particles in solution. And there had been previous work that allowed you to understand how sort of the size of the particle and charge on the particle. But there was a strong industrial reason to want to try to improve this method and get more out of it, which is that, nanoparticle characterization and quality control methods are quite slow and expensive, and, often involves either you're taking a sample and you're plating it up. If it's a biological sample, you're plating it up and you have to let it grow for 24 hours. So suppose that you're in the drinks industry and you want to know, have we had contamination by a bacterium that we don't want, that can cause food poisoning? You have to take that sample, you plate it up, you let it grow for 24 hours. Your line is going the whole time. By the time you know that you've got a problem, you've got to throw out a tremendous amount of stuff that you'd produced. It's very wasteful. If we can get a way that can detect those things sort of as they come through, then there's so much less waste in the system. And so that was one of the motivations. Another thing, when you're looking at contamination of other sorts, inorganic contamination, maybe what you've got to do is you've got to dry it out somehow, and then you've got to look at it in the electron microscope, and well, there are issues with that as well. So anyway, so the goal was to extract real-time shape data for particles in solution from the signal processing of the signal that they created. So basically trying to transition from this thing being a counting method to it being a rudimentary imaging method. And that's what we were successful at figuring out how to do. So this is sort of a picture of what happened. So this is not our device. This is the device that we did the original research on. We've got new devices now, but you can imagine that orangish stuff, that's what's called a pore. It's some sort of plastic material. And those green things, those are particles. And they're traveling along in some fluid through that pore from the top to the bottom along that Z axis, right? And as they go through, because there's an electrical current that's being carried by the solution, by the water solution, the salt solution that they're going through. If you put something there, then that's taking up room that the solution would have otherwise been in, right? So there's not as much solution flowing through, and that causes a drop in the current. So that's exactly what we see there, is that current pulse. And as you go through, you'll see on the right-hand side is like a single pulse, as a single particle is going through. And the really cool thing is that the shape of that pulse actually tells you something about the shape of the particles. It's sort of like a mathematical convolution process. You can almost imagine that it's like a scan, as you're scanning through the particle, right? So very cool to finally been able to do this. But let me tell you, there was an awful lot of engineering involved, because you've got to get the device to do what it needs to do properly as well. So this is sort of an area that I ended up getting involved with, and this is what my PhD students work on now, this sort of statistical metrology. And I love this slide about mathematics, statistics, science, and engineering. And you can imagine that all of these disciplines are working with some combination of the following. There's some sort of input that's put into a system, and that system is governed by the laws of nature. And from that system, the input relates in an output, right? That's what everything relates to that. Everything comes down to that. Now, if you're doing analysis or sort of, mathematical modeling, what you're taking are the laws of nature and the system you're putting it through and the input, and you're asking, what output will I get from this, right? Whereas if you're doing reverse analysis, well, that's when you've got the input, so you've got the output, right? So this is sort of what you're doing in a lot of situations. You know that you've got this output, and you want to know what caused that. What was the state that caused that, right? So if you do a COVID test and you get a result, what you want to know is what was the state that caused that result. Was it an infectious state, right? So again, you know the laws of nature and the system, and you know the output, and you're trying to deduce the input, right? Okay, now in science, you know the input and the output. You've done an experiment. You've designed a system, right? You've put input into it and you've put output. And from that, you're trying to figure out what were the laws of nature, right? And in engineering, and especially statistical engineering, what you've got is you've got an input. You want something. You know what the laws of nature are. You want a certain input to result in a certain output, and you've got to design the system that does that. So they're all sort of working with the same thing, but your goal, what you start with and what you're trying to figure out are different. And so I really, really loved this sort of statistical engineering question of how do we design a system that will give us good measurements, good statistical measurements. Really interesting area. Anyway, as I said, so many of the questions that my colleagues from chemistry and I don't know, biology and materials and all kinds of areas were asking me really actually came down to a question about measurement. Can I reliably measure shape, right? Whether that's shape of a nanoparticle or shape of a muscle. What about chemical composition? Can I measure the chemical composition of something? Can I measure anatomical variation that might be associated with an injury, for instance? Can I measure somebody's breathing pattern? That's sort of a film. You've got a film of how they're working. How can you measure that? And something that I think is really cool is that often we imagine that we're measuring some external and intrinsic property. And size is an example of this, right? We talk about size. We think of things of having an intrinsic, well-defined size, right? But quite often, size is what the instrument measures. That is to say, the thing you're measuring is defined by the way you have chosen to measure it. And this is particularly true of nano-sized particles. What does it mean to talk about the size? I mean, even if you think in terms of quantum mechanics, what would size even mean? If you're talking about some sort of cloud, what does it mean? You have to define what it is. And the question is, well, how are you measuring it? How are you measuring it defines what you mean. Are you measuring it in terms of forces? Are you measuring it in terms of how it moves, something called hydrodynamic radius, how it moves through water? Are you measuring it in terms of the way that it interacts with electrons in an electron microscope? There's so many different ways, and they're not equivalent definitions. So even trying to understand how does size as measured by resistive pulse sensing correspond with size as measured by electron microscopy? How are these related to each other? It's not a trivial question at all. And also you've got the question of how do we define measurements that are repeatable and precise and also predictive of outcomes of interest to us, right? Especially in the case where your measurement is defining your concept. You can't talk about a ground truth. There is no ground truth. There's no size, ultimate size. The only question is the thing I'm measuring a useful thing to be measuring? Does it tell me about something I care about, like whether this is going to kill a goldfish, right? Okay, So another thing I found is that doing impactful data science is really about stakeholder engagement, right? This is what it's called in industry, stakeholder engagement. You have to listen to people. You've got to respect them. You've got to respect that even if they don't know the same things as you do, and that you don't understand what they're saying and they don't understand what you're saying, that they know something and that's worth knowing and it's worth trying to understand. Also, you have to let their questions be the one that drive the work forwards. And it's your experience that steers it through the rough terrain, but the sort of motivation is coming from them, right? And you also have to focus on how to solve the problem and not just how to use the shiniest, fanciest new tools, right? And what you're like as a person is as or more important than how much you know and how smart you are, right? I'm certainly not the smartest mathematician and definitely not the smartest statistician. Remember, I only just learned it starting in 2011. I was definitely not the best statistician that had come to these people that I was working with across the university, but I was the first one who had ever actually stopped to listen to what they were asking and was willing to give them answers to the questions they were asking. So there's so much stuff to do if you're willing to let those people drive. And this is really where I felt like the jumping across the chasm was really coming in, which is that I was here in mathematics and statistics and I had my set of comfortable things. And it's really, you sort of try to sort of build out onto a, maybe a little platform off the edge of the canyon. They've got one of those at the Grand Canyon. It's terrifying. It's glass. You look down. Oh my God. So you can sort of build out from one side. But the only way that you're ever going to actually get some bridge between them is to shoot across to the other side and bring that rope with you, right? You've just got to make that leap to try to go to the other side and give up that control of being in your comfortable area. All right. So I transitioned to India industry. This was what I dressed like this on the first day. And everybody at my software company laughed at me because they all wear jeans and a t-shirt. Just want to say that was that's my transition to industry outfit. And yet that's actually not what industry dresses like. Okay. Anyway, so this is, I think often people ask, how could you leave a career in academia? And the answer was that I found that what I wanted to do was something that was easier to do and more valued in industry than it was in academia. And I think it's not that individuals don't value this, is that the system is not set up for this kind of work. But I think sometimes it feels very difficult to give up something you've spent a long time on. And this, this joke headline came up. So the sunk cost fallacy is, I've put so much into it already, I have to keep going, even if actually changing would be better for me. Anyway, so I like this. No choice but to see it through. This man is way too deep into trying to explain the sunk cost fallacy to give up now. Anyway, in summary, my unfocused career has spanned teaching, pure mathematics, metrology, applied data science, and has involved 3 employers across 2 countries. And let me tell you, as careers go, that's not that mixed up. There's a lot of evidence that most people who are now going into industry will have had 10 careers by the time they're 35 or 10 jobs by the time they're 35. It's very common. Data science, well, I looked at it actually. The term was invented before I was a graduate student, but it certainly wasn't something that everybody ever talked about. So my choices have been influenced by curiosity and desire to have an impact in the world, but also by changes in my personal life. And the fact is, I'm not the same person I was when I was in graduate school. Maths isn't the same thing it was. Industry isn't the same thing it was. And so for me to change, that was what made sense. I think quite often, especially in this country, I was just having a discussion beforehand with somebody about this. You get asked at a very young age, what do you want to be when you grow up? And then you go for your GCSEs and your A levels, and they're all about, where will your option choices take you? What's your ideal career? How are you going to get to that ideal career? And then what can I do with my degree, right? What sort of route are you going to take, right? And the fact is, this is from the World Economic Forum on the future of job and skills. I've blown it up on the next page. The most in-demand occupations or specialties did not exist 10 or even 5 years ago. And the pace of change is set to accelerate. By one popular estimate, 65% of children entering primary school today will ultimately end up working in completely new jobs that don't exist yet, right? And there's a great film called Did You Know? And they say we're currently preparing students for jobs that don't yet exist, using technologies that haven't been invented in order to solve problems we don't even know are problems yet. It's really important that you not get hung up on this idea of an ideal career you're aiming for. Just choose something that you think might be interesting for the next few years and keep your eyes open for new opportunities that seem cool. And this is the way to sort of float your way in an undisciplined way through, but doing really cool stuff along the way. So I wish you all fantastic careers, and thank you for having me.